Right, ma'am. Uh, okay, good evening again. So today we are going to discuss about predictive analytics. We made my presentation as simple as possible. If you have any doubts, you can stop me at any point in time. You can go ahead. That's it. The outline of my talk in, includes introduction first, then a brief motivation, then literature review related to that problem that is to be solved. And we will see the objective of our research in this regard, and we will see some of the algorithms proposed by our team related to predictive analytics. Then we'll start with conclusion. Right. Let us start with what is predictive analytics. If you look at data analytics in general, there are many types of data analytics algorithms. One type is descriptive data analytics. The second one is diagnostic data analytics. The third one is predictive data analytics. The next one is prescriptive data analytics. And they are all, complex in the order in which I read. And descriptive is so simple, which means finding some statistical features like mean, median, mode, standard deviation, cutoffs, and moments, and so on, and trying to understand the data in a descriptive way, either textual way or graphical way. And slightly more complex task is diagnostic data analytics, in which, given the data, we need to find what exactly has happened. For example, if you look at the marks of the students scored in a particular subject, finding just class average and the frequency distribution of the marks and all is basically called as descriptive. Diagnostic, suppose we see that class average is so less, finding out why the class average is so less, so that is diagnostic. Whereas predictive means, suppose some student has scored some marks in test one, test two. What is the mark that he will score in the third test or fourth test, and so on. And similarly, if you take, the sugar level, sugar reading, suppose after 1 hour, after the food 1 hour, if you take the sugar, reading, then again 1.5 hours, and then 2 hours, and so on. Then, if you want to know without reading the blood sugar level, if you want to predict what will be the blood sugar level after 3 hours, then it is called as predictive. And prescriptive is that if you set a goal, right, to reach the goal, what is there we have to do? Doing that analysis is called as prescriptive. For example, doctors are giving prescription, and the goal is to cure the disease. And what is that medicine that's to be taken to cure the disease is prescriptive. And we will look at the predictive analytics in this lecture today, and which means process of predicting future events using the historical data. Future events using historical data. Right. And there are a lot of use cases, applications for predictive analytics, namely in retail sector, banking sector, sales, social media, advertising, and healthcare, and so on. For instance, in retail, if you look at different components associated with retail, inventory is one component, supply chain, marketing, campaign, behavioral analytics, customer journey analysis, and customer personalization. These are all different types of things that are normally looked at in retail market. For instance, in inventory, we need to plan, how much items are required to be there in the go down after 1 week or after 1 month, and so on. In supply chain, you need to predict the probability of getting the commodities that we ordered in time. And for instance, in the market analysis, we need to look at how much that items will be sold in a week time or in a year time and so on. In market advertisement, right? There, suppose you advertise in social media, particularly, in Facebook, let us say you are advertising how many more number of customers you can attract for your business. Suppose you advertise in newspaper, how many more customers you can attract to your business. These are all, marketing campaign. And behavioral analytics means that if a customer comes today and buys a particular items in sequence, what is the probability that he will buy next item? That is basically behavioral analytics. Somebody who buys cricket bat may also buy cricket ball, right? So kind of behavior, the pattern will be there. And customer journey, number of customers who can come on a particular day. For instance, during weekends, more customers will come. On other days, less customers will come. To find out pattern of customers' journey coming and going, will help the business to plan in a better way. Customer personalization. A particular customer, will buy things, come for shopping in a particular way. For instance, if some people will come for shopping on Sundays, some people will be coming for Sundays, Saturday, Sundays, right? And very few people will come for shopping on weekdays. And but if you look at a particular person, you will have particular interest in shopping. So if you can understand this particular person's interest in shopping, then we can give target advertisement through mobile phone or whatever. And for all this, predicting the behavior, the pattern, the requirement, and all that are required, and they are basically called as predictive analytics. Right. So we understood what is predictive analytics. Given the historical data, predicting what is going to happen in the future is called as predictive analytics. And in this lecture today, we will look at one particular prediction problem called adverse drug reaction problem. So what is it? When you take a drug, right, it may cure disease, but it may produce some other disease. At least, a lighter disease it may produce. For example, when you take a tablet for fever, it may bring, a headache, or it may bring, sleepiness and so on, right? Such hazardous events are called as adverse drug reaction. Right. Given the drug, how do you find normally whether the drug will cause abnormal, reactions or not? Usually, the drug manufacturers will give the drugs to animals first and find out if it is creating any adverse reactions or not. And once it is successfully tested with animals, then they will go and test it with old people in maybe underdeveloped countries, and then they will bring it to the other groups. Slowly, they will bring it to the public, the whole mass, right? Normally, it will take huge amount of time, for testing a drug before coming to the market. But if it is tested to some extent using computer, then the time taken for testing the drug for side effect will be minimized. And this is what we are going
Okay.
to discuss
First, you have
today.
to simplify that.
How do you make a model?
That's the problem. You multiply, and you bring this equation.
Excuse me,
So
can you please mute your mic? Thank you. Right. Right, you may be wondering why this ADR is very important thing. In India, in a particular year, 232 ADR cases were reported, out of which 36.21 percentage of people had the harmful effect of the adverse drug reaction, and the remaining are harmless. So we can say that almost one third of the adverse reactions are harmful. Therefore, if it is not predicted properly even before it is administered, then it may cause serious problems. And another issue with this ADR research is that most of the ADRs are not reported. Out of 100 people who have taken drugs, let's say some 10 people are getting some side effects. Not all 10 will go and report to the doctors. some more, maybe one or two will go back to the doctor saying that whatever drug that you gave created extra issues, all that, and the doctors will record in his medical history. And sometime, the customers who took the drugs got the side effects will go and write in the social media, and but some people may not do that at all. So many areas are not reported. That is a very big challenge in understanding which drug will cause ADR, which drug will not cause ADR. And usually the drug development process is costly, and because it takes a lot of time, we need a lot of human samples, and you need to pay a lot for them and all that. So it's a costly effort. And predicting areas in the early stages of developing drug will help the drug manufacturer a lot. Let us look at how the adverse drug reaction will come from. What are the sources from which they can be obtained? One is clinical data. The other one is non-clinical data. In clinical data, we have electronic health records where the doctors would have mentioned when people took this drug, and a particular patient took this drug, he reported these side effects, right? That is electronic record. Sometime, the person who took the drug may have some side effects, he will go and write it in the social media. And that is another source from where we can get this information. Coming to non-clinical data, if you look at the chemical component of the drug, and there itself, you can say it may possibly cause some side effects or not, some biological behavior, phenotypic behavior, and all that we can look at. Coming to the literature related to this ADR prediction, people have worked extensively, and people have used different data sets, and they used different features, and then they reported AUROC score. You can see that AUROC score is ranging from zero point 0.9 something to even smaller values like 0.48 and so on. And different databases are used. For instance, this guy has used 1430 drugs and 1766 ADRs, meaning some drugs may cause ADRs, some drugs may not cause ADRs. If they cause, they may cause one or more ADRs and so on. And to predict the ADRs produced by a drug, this guy has used structure information. Similarly, every guys in the literature used the different properties of the drug, or properties of the patient who administered and all that. That is called as biological thing. And some people have used something known as the target. Target means the drug is basically chemical, right? It will go and get attached to some portion of the body, that is called as target. Indication is basically, because of the symptoms only, doctors would have given the tablet, right? And the symptom is called as indication. And the molecular structure, chemical structure, and combination of several other things like targets, indications, all that are considered as features by different people. They reported different AUROC scores like this. Well, one big issue of this all the studies reported in the literature is that they took the areas that are available in the social media and also maintained by various governments, but they are all under-reporting areas, meaning many areas are not reported. That is one issue. Another issue is that the number of positive samples is very less. So these are the main issues identified in this literature. So therefore, it is required to propose a novel method for predicting ADRs by balancing data set. Why we need to balance the data set? Number of positive samples is so less compared to the number of negative samples. And in one work, we proposed an idea to balance the data set, and we made some ensembling models, and then we predicted the ADRs. In another work, we built something known as knowledge graph, and using knowledge graph, we predicted the adverse reaction. Any queries so far? Some participants can say yes or no so that I can understand that whether I'm connected or not.
Yes, sir. Yes,
Fine.
sir. We are
Okay,
able
good.
to understand.
Fine. Right. There is a database called CIDR database, and which is used by many researchers in this field. We also took that CIDR database, and CIDR also, there are many variants, and we took CIDR 4.1. This contains 1,430 drugs and 6,123 ADRs, and also 1,66,128 unique drug ADR associations. Meaning, a drug is causing on a particular area, then it is making one association. Like that, 1,66,128 unique drug ADR associations are reported in that dataset. The dataset contains drugs in the form of IDs called stitch ID and the corresponding ADRs. And we also used PubChem dataset, and there the data are stored in the form of something known as SMILE, which stands for Simplified Molecular Input Line Entry System. What it basically means is that given a drug, a drug is basically a chemical component, right? That chemical component is written as a sequence of ASCII characters, and that sequence of ASCII characters representing the chemical structure of the drug is called as um, SMILE, Simplified Molecular Input Line Entry System. Well, so this table shows the ADR with positive and negative details. There is an ADR called acute renal failure. It's basically a ADR, adverse drug reaction. And among all the drugs that are reported in the database, 201 drugs are having that particular ADR, acute renal failure, and 1,226 drugs are not reporting this particular ADR. Similarly, for other diseases like GI bleeding, acute myocardial infarction, acute liver injury, for all these different areas, different number of positive samples, different number of negative samples are there. You see that the number of positive samples is so less. For instance, the last one, acute liver injury, only 4 positive samples are there. 1,426 negative samples are there, meaning only 4 drugs are found to cause this ADR. That is natural, right? Drugs will not cause too many ADRs, and not all drugs will cause ADR. So, what is the problem it is posing? You suppose you build a machine learning model taking this data and it will bias to the majority. You have heard of the story. When somebody built a machine learning model to identify the criminal, given features of the persons and identifying whether he is a criminal or not. In the US, the model which was built was always saying that black people are criminals. And the reason is that in the database they are majority, and based on the majority, the model has learned to be biased to tell that black people are biased. So it's completely unacceptable, and so that sort of things is expected if you have unbalanced data set like this. Somehow we need to make it balanced. So how do we extract the features? How we build the machine learning models? We'll see. There's a package called RDKit in Python. So what that does is that given the smile string as input, sequence of ASCII characters as input to this RDKit tool, this will give the features of each atom in the molecule which is represented by the smile string. Right? For every single atom, it will give 68 features. And how many atoms will be there? In the CIDR data set, when we look at all possible drugs, and the maximum number of atoms that are there with molecule representing the drug is 58. Therefore, therefore, for every drug, we get a feature vector, which is basically a 2D array, which is of size 58 by 68. 58 atoms are there. For every atom, 68 features are constructed by the tool which is available in Python. And so for every drug, the feature vector representation is a matrix of size 58 by 68. And we eliminated some data from the data set. Any areas with less than 10 frequency is removed from this. The reason is that it is not reliable, right? So some errors may be there, and based on small frequency, if we say that ADR is there, then that's not correct. So excuse me, mute yourself, please. Okay. Right. If you have any queries, you can ask me. So what you see is the chemical structure representing a drug. And this is basically the sequence of ASCII characters representing the drug molecule. And this is called as smile string, right? Corresponding to the smile string, you get a matrix, and this matrix is basically this feature vector for this particular smile string or this particular molecule, right? So every drug will have a matrix like this. So what is it? So every drug will have number of atoms. For atom 1, 68 features will be there in the first row. For atom 2, 68 features will be there in the second row, and so on. Suppose a drug has got less than 58 atoms, then the real part of this matrix will be zeros, right? And what if a drug has got more than 58 atoms? In the cited data set, the utmost number of atoms that are there in the molecule representing the drug is 58. Therefore, 58 rows are kept here. Right. Now, the primary question is that how to manage imbalanced data set. There are many ways. Some people have done some data augmentations, and, and what we have done is a slightly different method. Maybe I'll show you the graph and let you understand that. Let's say this is a database with positive and negative samples, and this blue color portion represents positive, the yellow color portion is representing negative data in the data set. So what you see here is that number of negative samples is too many, meaning uh, drugs not causing ADR is too many, drugs causing ADR is so less, right? So much of imbalanceness is that. So what we did is that we took this blue portion, kept it here in a new data set, and that much from this yellow we cut it and put it off here. Then the same blue is coming here, and the next yellow portion is cut and put it off here. So like that we framed many data sets like this, where each data set is balanced one. You can see here, right? Let's say this blue color is only 10, and this yellow color is 100. Top 10 in the yellow, and this 10 will be put here, and next 10 here, and this 10 will be put here, and next 10 here and put here. So like that you can generate 10 data sets, right? And all the 10 data sets are balanced now, right? But you may be arguing that this blue color here and blue color here are the same, and what is extra information will you get? We will run or build a model only on this first, and then this, and then this, and then this. Then we will take the collective opinion of all the responses given by all these models. Right. So for that is how we are managing imbalance data set. And in each small data set, 80% is used for training, the remaining 20% used for testing. And we build a support vector machine on this 80%, and then we test this support vector machine on this 20%. As you see here, one SVM is built on this, that is called as SVM1. Another SVM is built on this, called SVM2. Another SVM is built on this, called SVM3, and so on. What is this optimal SVM? We are doing hyperparameter tuning. SVM can be linear or non-linear, and for each one, there are some other parameters, right? And hyperparameters are found based on some built-in function available in Python tool. There is something known as random search algorithm for finding the this possible hyperparameters that we used. Now the question is that we built K models, then how do you combine them? As you know, there are methods like boosting, stacking, and all that. And so what we have done is that we have taken the voting. Both there are two types of voting. One is soft voting and another is hard voting. We took the voting of all this. What does it mean? Once you train these models, given a drug, you can get the smile string using some method manually. Once you get the smile string, that you can feed that into the RDKit and Python. That will give the future vector matrix of size 58 by 68, and that will be fed into the SVM1. That SVM will give whether side effect is there or not, yes or no. Similarly, for this also, we will give this will say yes or no and so on. Now we'll see what is the majority, right? Majority says yes, then side effect is there. Majority says no, then side effect is not there. This is basically called as hard voting.
That SVM, can you explain a little bit about SVM, as I don't know about this SVM, what is that? Just we know that support vector machine, but
Yeah.
what is that support vector machine? What it does?
Well, okay, I'll have to use my pen. I'll do that. Right. Let us look at linear SVM. That is a bit easy to understand. Second. I'll use Microsoft Notebook. Okay, I'll try to write in PDF as. Hold on. Or maybe I'll explain without. Okay. Are you aware of the classification, binary classification? Given future vectors representing objects, we need to classify into two categories. Are you aware of that?
Yes, sir. Yes, sir.
Right. Good. Right. So, in that, we need to draw a straight line which is
The line.
separating feature vectors of two different categories, right? So that is normal classifier, right? But in support vector machine, we will again draw line, but with some extra property. The extra property is that the distance between the line and nearby vectors, they are called as support vectors, nearby vectors, is maximum. The distance between the line drawn and the nearby vectors either side of the line is maximum. Right?
Okay.
Right. If I draw, then it will be better, but I don't have the Microsoft Note. Okay. Okay.
If it is maximum, then what will happen, sir? You're
Yeah.
saying that
The advantage is that when you give the margin high, right? When the test case is happening, and you will get less error in classification.
Okay, sir.
Okay, 1 second. If I give me 2 minutes, I'll try to write it. Uh, can you see the screen now?
Yes, sir. Yes, we are capable of seeing.
Let's say we have data. Every box is representing one data. Another class of objects represented by this X. Something like this. So if you're, this is given for the, building the model. During training, you are given this data, right? Suppose you don't want to use SVM, you may get a straight line like this, right? Separating these two data. Now the training error is 0, right? Because all the objects of one class are put on one side, and all the objects of other class put on other side. There is no testing error at all. But what happens is that when a new example comes, let's say some, right, X comes, or box comes, we'll see what happens. Suppose that box is present here, right? And this box has come during testing time. According to the model that is built, you will say that this box is X, right? Let's say this is object 1, all this, these are all object 2, right? And you say this box is object 2. Okay, that is incorrect, right? So although the training accuracy is 100%, the testing error has come. On the other hand, instead of drawing a straight line that way, if you draw a straight line like, you take, for instance, take this length, let's say this 10 unit, and just cut that 10 unit at half. Suppose this is your straight line separating this data from this data. Then when this comes during testing, that is classified correctly, right? So it is better to give a margin as much as possible, right? What is your margin? For the straight line, take the closest sample from this class, closest sample from this class, right? And suppose this, find the distance between these two. And if the distance is, let's say, 10 unit, and at 5 unit, it should cut. The straight line should cut. And this is called as support vector mission decision boundary. And these two are called as support vectors. Support vectors, right? So this is how support vector is better than the normal classifier. Got the point?
Thank you, sir. Thank you, sir.
Right. Let us move on to presentation. So in our case, support vector machine will tell the object has got the drug has got ADR or not, right? Above the straight line means ADR has happened. Below the line means ADR does not happen. But the problem is that many SVMs are there. Everyone will say yes or no and find out whether yes is majority or no is majority. Based on that, you take the call. Based on majority, you take the call. That is called as hard voting. What is soft voting? Soft voting means giving the weight for everybody's response and taking, weighted sum. Based on the weighted sum threshold, you decide whether the drug is causing the ADR or not. So separate model is created for each area, right? And suppose there are 100 areas in a data set, 100 models are created. That is one of the drawback of this method. Although the accuracy, precision, recall, AEROS score all are good, and separate models are required. That is a big issue. And you need to run all the models separately. And as you know, the performance metrics are defined using something known as confusion matrix. Just look at this portion. Right. The row says the actual prediction. The actual prediction is yes means first row. Actual prediction is no means the second row. And the column says the ground truth. Ground truth is S means first column, ground truth no means second column. So the prediction, ground truth. Suppose prediction is matching with ground truth, that is called as true positive. The prediction is not matching with the ground truth, where the prediction says yes, the ground truth says no, that is called as false positive, right? It is predicted as positive falsely. Similarly, when the ground truth is yes, but prediction is no, it is called as false negative. And when the ground truth is no and the prediction is no, it is called as true negative. Right. And based on these four data in the confusion matrix, we define other metrics like precision, recall, F1 score, true negative, and all that. For instance, precision means true positive divided by true positive plus false positive, and recall is true positive by true positive plus false negative, and so on. And why all these measures are essential, not one is sufficient, is that, for some application, precision itself is good enough. For some application, recall is good enough. And for some application, both are required. That is where we need to use this F1 score, which is basically the harmonic mean of this precision and recall. Right. For instance, when the data set is unbalanced, for instance, in our case, we have a small number of positive samples and so much of negative samples, right? And unless the recall is good, then the model cannot be, told as good model. You know why? Assume the case that we have only one positive sample, 99 are negative samples. Suppose I give a random, I give some algorithm which is not looking at, the data, input data at all. I give always, right? Negative, 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 negative. How many times I'll be correct? 99 times I will be correct out of 100 times. Only once I will make mistake. Although I'm not even looking at the input, I'm just saying negative, 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 negative. I am correct 99 times out of 100 times. The accuracy is 99%. Therefore, accuracy alone is not a good matrix measure. We need to look at the recall also. And the F1 score is basically the harmonic mean of precision recall. That is assumed to be a reasonable metric. Let us look at, how much accuracy, precision, recall, all that we get. In the first column, the ADRs are reported. For this ADR, this is the ADR number. For instance, this may be corresponding to some liver injury and so on. And the accuracy we got is 0.975%. Accuracy is 0.975 and sensitivity is 0.982. specificity is 0.968, precision is 0.968, and so on. AROC is 0.975. Like that, for each of the ADRs, the data is reported. Out of all this, AROC is a better metric. You can see here it's all more than zero point 0.9, which is indication that the model is doing good. The maximum value of AROC is 1. It is close to 1. So when it is compared with the existing models, so the ensemble SVM is the proposed model, and Day et al. Has given the model which is the best known literature before the advent of our model. And you can see in terms of accuracy, the competing model is better, not our model. In terms of sensitivity, our model is better. And in terms of specificity, the existing model is better. In terms of precision, our model is better. And in terms of AROC, their model is better. So for the first ADR, but for second ADR, ours is better in all. For the third ADR, ours is better in the second one, and here and so on. So if you look at all these ADRs, in majority of the cases, our model is better than the the existing model, competing model. Of course, we are not able to beat the existing model in all metrics for all ADRs, but for majority of the ADRs, for majority of the metrics, ours is better. Therefore, it is publishable one. Okay. Um, so in terms of MAP, mean average precision, the existing model is 0.523, and our model is giving 0.989, which is a significant improvement. Right. And we also give some other results for accuracy. How many drugs are having accuracy 0.8? 460 drugs are having accuracy 0.8. How many drugs have got accuracy 1? 61 drugs. How many drugs have got accuracy, let's say, zero point 0.4? 91 drugs. So what it basically says that this accumulation is happening at the right end of this accuracy spectrum. So suppose this is happening here, then we can say that it's poor since it is there, and majority of the drugs are falling into a good accuracy category. Therefore, the model performance is okay. And even for precision, the same thing is happening, almost similar thing is happening. For sensitivity also, you can see majority of the drugs are giving 100% sensitivity. And specificity, it is spread, but the peak is there at zero point 0.6, so that's a good indication. For FN score, you can see the lowest itself is somewhere here, 0.6, and it goes up to 1. So FN score is better for all drugs. And AROC is also good. You can see it is on the right end of the spectrum. So the model performance is justified because of this charts. And this database independence test is also important. What happens is that although we are using 80% from the dataset for training, remaining 20% for testing, when the model trained on one data set is taken to other data set for testing, then doesn't work well. It is working well for the remaining 20% when it is used for test. But when it is taken to other completely new data set for testing, it is not working well. Most of the cases, most of the models. So, but what is the problem with that? Because of that, you cannot deploy that model because generalization capability is not there. To ensure the generalization capability, it is better to test on a nearly different data set. And when we did on some new data sets with these ADRs, acute liver injury, GI bleeding, acute renal failure, and so on, and we got the sensitivity like this. This is competing method is better than ours in terms of acute liver injury. But in term for the ADR bleeding, ours is doing better. For this also, ours is doing better. For this also, ours is doing better. Out of 4 ADRs, 3 are in our favor. Again, just saying the database independent test is not good enough to, ensure the model's credibility. Uh, what we need to do extra is that some explainability analysis we need to do. And there is something known as sharp features, and that is basically giving the explainability of the model, why the model is performing well, because of which feature the model is performing well. Just look at this formula. This is the formula used to give the SHAP feature. And this formula, just look at this term first. So you see F is set of all features, right? And in that set of all features, we removed this K. K is a specific feature. So take the feature set and without K, with just take the feature set F without K, and this is including F and K. So take the the model performance for this feature set F along with K. Take the model performance for this F alone, which does not include K, and find the difference between the model performance, right? If the difference is more, then you can say that including the feature K is more important, right? And if the difference is less, then you can just drop this K. K is not that important, right? So this difference is basically, quantifying the importance of adding the feature K or importance of feature K in the feature vector, right? And this is basically normalizing factor, out of this many number of subsets of features, n minus 1 c mod f is basically the number of times that you need to find the differences for various subset of features. And therefore you need to sum all those differences divided by number of times that you found the differences. And then you sum that, and then finally you divide by n, where n is the total number of features, and whatever that you get is basically called as SHAP feature, right? So this SHAP feature will tell importance of feature K. Phi K is the SHAP feature value for the feature K, right? And you can see in the next chart. So these are all feature numbers. In a feature vector, we have feature 1, 2, 3, and so on up to largest index feature, right? This is a large. You can see for this feature 1359, you can see the length is more. The length says the importance of this. What is that importance? This 5K is basically means the length here. Pi k is large, then the feature k is very important. So this is the best feature used. This is second best feature used, and so on. And this gives explainability out of uh, so many features that we have, and which feature is more important. You can find out like this, and then you can interpret that with the real world scenario. So, what is the drawback? The main drawback is that for every single ADR, you need to build a single model. If there are 1,000 ADRs, you need to build 1,000 models, SVM models. So that is time consuming, and even the testing time will also be very high. And chemical properties alone is used in this model, and it is better to use some extra features along with chemical features to improve the performance. So therefore, in the model 2, method 2, we use non-chemical properties also, and we try to make a one single model for all the areas together. So here we use something known as knowledge graph. What is knowledge graph? What you see here is called as knowledge graph. As you know, graph consists of nodes and edges, right? In this knowledge graph, every node represents either drug or indication or pathway and gene and so on. And what does the age mean? If there is an age between a drug and ADR, it means that the drug is causing that ADR, right? So that is how a knowledge graph is constructed. And the knowledge graph will be converted into some feature vectors by using algorithm called node-to-vec. This node-to-vec algorithm is basically a neural network, and it will give for every node, every edge, corresponding feature vector, and those feature vectors will fit into the model, and the model will get trained to understand the relationship between feature vector and the label of the drug. The label of the drug is ADR is there or not, right? And then finally, the trained model will be used for testing purpose. That time we will extract the features using node to algorithm, and we'll feed the features to this model, and this model will give yes or no. This model is basically neural network model. Right. Let us get into the details of the knowledge graph. There are 6 types of nodes allowed in the knowledge graph. One type of node is drug, and another type is ADR. Next type is indication. Next type is target protein. Next type is gene interaction, and next type is pathway. These are all 6 different types of nodes, and there are 5 different types of the edges. And has ADR is an edge which is connecting drug and ADR. Has indication is an edge which is connecting drug and indication. What do you mean indication here? Doctor would have given the drug because of some indication or symptom, right? That is what indication means. And has target, if the drug has got target to a particular area in the body, then there's a match between the drug and the target name. And has gene, if the gene is present, then the drug has got the drug is associated with the gene, then there will be a link, otherwise it is not. Has pathway, if the drug is going through a particular pathway, then there's a edge between the drug and the pathway node.
இப்ப ஷேர் பண்றாங்க ஸ்கிரீன்.
Yeah. Any query?
So these nodes will be connected to this edges, is it, sir?
No.
The
Edge will be
signs,
connecting nodes.
Edge, every
Edge
edge
will be
will
connecting to nodes.
nodes.
Right.
What will be the
Implication,
uh,
interpretation. Right. See, suppose there's an edge from drug to one ADR. The interpretation of that is that drug is causing that particular ADR. Understood? See, in a graph, we have only 2 components, nodes and edges, right? And in the database, we have number of drugs, number of ADRs, number of indications, and so on, right? For every drug, you make one node there. For every ADR, you make one node there. For every indication, you make one node there. For every target in the database, you make one node there. Like that, for each of these 6 categories, you make one node. Now, you connect 2 nodes if there is an association reported in the database. For example, the database, we say drug D1 is causing ADR A1. Then the node D1 is connected to the ADR A1. Okay.
okay, sir.
Right.
Okay.
Well, so the database details are given here. The number of drugs used is 7,219, and the number of ADRs reported in the database is 5,469. Indications this much and this much, target this much, and so on. And the total number of entries is 22,499, and number of associations with drug, right? Meaning the number of edges. Number of edges are this many. Number of edges from drug to ADR is 1,12,000 something. And number of edges from drug to indication is 1,20,000 12,141, and the number of associations, meaning number of links or edges from drug to target, is 17,600 and so on. So the summary is that the knowledge graph is built from the data available in the database. And this just schematic representation of knowledge graph. Every blue circular disk, right, represents a node. That node may be representing drug or ADR or pathway and so on. And the edge connecting two nodes means that there is an association between those two nodes. What do you mean association? If a drug is causing ADR, there's an association, right? If a drug is going attached to some particular target in the body, then there's an association between the drug and the particular part in the body. Well, maybe due to want of time, I skip this math. So just I give the outline. There is an algorithm called node-to-vec algorithm, which is basically using ANN that will take a word as an input and give the representation of word called embedding as output. And in this case, each node in the knowledge graph is basically a word, right? How node is word? As you know, node can be represented by a matrix, right, of size 58 by 68, right? And the whole matrix can be considered as a word by concatenating every element one after the other, and row after row. We can make it so we can make a big word, right? That word, if you give to that ANN, and that ANN will give a representation of that particular word, and such an algorithm is called as node-to-vec algorithm. And let me skip this small math part. And there is something known as continuous bag of words, and the node to vec will give the representation, right? And there will be some dictionary of representations, and given the knowledge graph and how many times every word in the dictionary comes, that frequency distribution is called as word the bag of words. And that frequency distribution of words in the dictionary are used as a feature vector, and that is used as a feature vector for drug and used feature vector for ADR. And for the drug, the feature vector size is 800, and for ADR also feature vector size is 800. When you concatenate these two, you get 1600, and that goes to the first layer in the neural network. And this is our simple architecture, our own architecture, and all are made as fully connected, no convolution layer. And the final layer has got only one node, right? If it fires the output, then it is yes. If it doesn't fire the output, no. Meaning, there will be a threshold. The output is more than the threshold, then it is yes. And if the output is less than the threshold, the output is no. One reason why we went for this is that we are dealing with 1600 inputs, right? Node size is 1600. Therefore, we need to have a large thing initially. 1600 nodes are connected to 1024 nodes, and then we need to go to smaller quickly. Therefore, we reduce by half of every time, and then from this we made it to one. So this is one way of making it to reduce the number of outputs less. Sorry?
Sir, from 1024, you are going to 512. That is half of that. Okay. What are the things that we have to leave, and which one we have to keep it as such to the next layer?
Right. See, building the layers is basically an art. And many a times, we will make some layers, and if it is working, we'll keep. Otherwise, we'll drop and we'll try the remaining things, right? And see which one is working well. We will figure it out. But how we built is that our objective was to, reduce this very quickly, so that you will end up getting a small number of layers, right? And suppose 1024,800 means the depth of the network will be more, right? So we don't want to keep more number of layers. That is why we reduce by half every time. You can say that exponential amount of reduction, right? and which is to be dropped, which is to be kept. We are not doing fine tuning, like dropping the neurons or dropping the layers. All that we didn't try. Of course, we tried with several other architectures, and we found that this architecture is giving good result. Therefore, we are reporting. But in general, to answer your query, how to keep some layers, or when to drop some layers, when to drop some neurons, when to retain some neurons. You know, we have to do it using trial and error method only, because the explainability is not good in neural network. We don't know the interpretation of the data that is coming over here. Of course, here we know, but once it passes through one layer, we don't know, the meaning of the data that is coming in. So therefore, we need to randomly drop some neurons, randomly drop some layers, and see how the results are changing to be good or changing to be bad, and so on. Luckily, we have a lot of tools in Python toolbox. Just call those fine tuning functionalities that will try out various combinations, and it will bring you the locally optimal architecture. Otherwise, there is
Thank you
no,
for it.
yeah, there is no, strict method by which you can get the best possible, architecture. Well, so if you take, for example, the edge connecting drug and ADR, this is an edge information, and this many number of, you know, drug to ADR combination is coming, and similarly, for this drug to indication, this many combinations are there. Each one should be embedded, meaning you need to have the feature vector for each kind. For this, every occurrence of this one feature vector, every occurrence of one this feature vector. These are all number of feature vectors, and the classifier was trained using this many. And for testing, we took a separate number of drug ADR pairs, and similarly for training, in this case this many, and testing this many, and so on. So the results that are obtained are shown here. And when we make one-fold validation, we got accuracy, precision, recall, IEROC like this. Two-fold this, three-fold this, and so on. And we took the average of all this accuracies, precision, recall, we get this much. So since AEROC is 0.912, you can say that the model is performing well. So I hope you all know what is fold means. See, the fold means we need to, train the model only once and test means one fold. Training the model two times and testing is twofold, right? And testing, training model three times and testing threefold. So what do you mean by training model two times, for instance? What do? You take the training data set into two, and with the first part you train, and second part again you train, and get the results, right, and take the average of that. So that is what given here, right? When it is k-fold, you divide the data set into k-fold, k sets, and drop one at a time, and train with others, and test with the dropped one, like that. Well, and when we try to compare our results with the existing results, we saw that precision is better than their result, and recall is also better, F1 score is better, and AU is also good. But the accuracy they have not reported. We got accuracy of 0.832. And when this is compared with other existing methods in the literature, you can see that AROC score of the proposed method is better than the existing methods. So for various drugs, for various ADRs, the reports are given. This hydroxychloroquine, it's a drug given for COVID affected people, and that drug is known to cause these three ADRs, and our method is able to predict with AER score of 0.11 only, uh, right, for the first one. For the second one, the AROC score is 0.87. That is good, very good. And for the third one, AROC score is 0.683. These two are okay, but the first one is not that great. But however, this is better than this, and in this case, theirs is better. Out of three, in two areas, we are better than the existing one. And similarly, there is another medicine given for corona affected people, azithromycin, that is known to cause these two ADRs, and our method is predicting those two ADRs with this much AEROC, which is much better than the competing methods AEROC. Like that, chloroquine also, no, uh, colchicine. Also, we tried remdesivir. We tried we tried riba ribavirin. We tried. So in all this, you can see in majority of the cases, the proposed model, our model, is better than the existing model, but not in all cases. And other drugs are also mentioned here. And in majority of the cases, the proposed model is better. Okay. And this one shows results on some other data set and called TLEAD data set, and their total drugs using knowledge graph is shown here. This many drugs are considered, but out of this, only this many were used for knowledge graph building, and the computing method is giving this much AROC. Our method is giving slightly better. Here lesser, here better, here better. So out of four, thing, in three cases, ours is better. Right. The conclusion is that predicting the ADR associated with the drug is a very challenging problem. Usually, it is we need to consider the context information for predicting ADR more efficiently. And the knowledge graph embedding is found to be a better method than the ensemble SVM methods, and the neural network, which is used there in knowledge graph for word embedding, is proved to be as a good method, and the proposed method has significantly outperformed the competing methods, which proves that the addition of pathways and genes to the knowledge graph has helped in better embedding. If you look at the first model, there the additional informations were not used. In the second method, the additional information were used. Because of that, we got better accuracy, precision, recall, AROC score on that. And each one of these methods was published in one journal, and these are all the references. I'll stop for some 5 to 10 minutes. You can ask queries, not just related to the presentation. In general, also, if you have any queries related to ML, AI, generative AI, you can discuss with me. If I know answer, I'll give you. Otherwise, I'll find out and give you later.
Thank you, Professor. It was an excellent session. Faculty members, please raise your questions. Professor is ready to answer. Participants, any questions from your side?
Time to sleep.
I think no more questions from participants, Professor.
Okay, thank you. Somebody is raising hand.
Arif sir, any
No
questions
question,
from your side?
Sir, good evening, sir.
Good evening.
Sir, on some curiosity I will ask, sir.
Hmm.
Sir, I'm doing PhD in VLSI testing.
Okay.
So how can related to then prediction through through the testing process belongs to medical and through ML algorithms, sir? Any other major algorithms there, sir?
Can you repeat your question again?
So through the machine learning algorithm
Hmm.
and VLSI testing, sir. So how can be related to?
Okay. Okay. So you are doing VLSI testing. You're
Yes, sir.
asking how to use machine learning or predictive algorithms for
Yes, sir.
testing VLSI, right? Okay.
Yes, sir. Yes.
Right. So when you do VLSI testing, you are testing for the correctness of the circuit, or you are predicting the energy usage or the space usage and so on.
Yes, sir. I'm putting that area and delay, sir.
Energy, right? Energy, right?
Yes,
Right.
yes,
So what you can do, you can look at the historical data for
yes, sir.
different, models of VLSI, how
Yes,
much, space was used in the past, and that association you can learn through ML model, and then you can predict, given the, hardware, how much space it will take or how much power it will consume, right? For that, you need to have the data set, historical data.
okay,
For
okay.
example, VLSI, hardware has got a number of components one, components two, and so on, right? And corresponding to that, how much power was used, how much space was used. If you know that details, relationship between the components in VLSI and the power usage can be learned, and components in VLSI and the space usage can be learned, and that learned information or learned model can be used to predict the power and space for the given VLSI with number of components in every time.
Okay, 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 sir. Thank you, sir.
Right. There are many algorithms that are already available there, where you need to go through the literature and try to understand how those algorithms are developed, and then you need to come up with your own algorithm. You should not try to use the existing algorithm. You should come up with your own algorithm. That you can do only when if you understand, the recent 4 5 such algorithms, and find out where it is not working well, why it is not working well. Then you will have some intuition to have your own algorithm to overcome those limitations.
Yes, sir. Yes, sir.
Right.
Thank you so much, sir. Thank you, sir.
So, any other queries?
Any other questions from participant side? Please raise your questions. Professor, I think no questions from participant side.
Okay, ma'am.
Thank you, Professor. Thank you for being part of this online FDP program. Thank you very much, Professor.
Thank you, ma'am. Thank you. Thank you, all the participants. All the very
Sir,
best.
sir, I have one doubt, sir.
Professor, I think one person is asking for a query.
Yeah. Please, please.
Sir, please
Sir,
go ahead.
sir, when we are developing a new algorithm, or that compared with any other hybrid algorithm, so what are the hyperparameters we can include? Can you give me one simple example how to develop a new algorithm? Small example, sir.
Right. How to develop new algorithms?
Yes,
That is
sir.
one question. And how
Yes,
to
sir.
tune the hyperparameter. Second question, right?
Yes, sir.
Okay.
Yes, sir. Yes, sir.
See, algorithm design is basically an art. So there is no algorithm to develop another algorithm. In other words, there is no fixed procedure to develop an algorithm. Okay, so you need to have intuition. Based on intuition, you have to develop algorithm. Having said that, what you can do, you can look at various algorithms available in the literature and see how one algorithm is different from other algorithm, how one algorithm is better than the other algorithm. That difference, if you can recall and grasp, later you can write your own algorithm, something like this. If you can solve 10 problems, 11th problem you can solve if it is very similar to first 10 problems, something like that, right? There's no fixed rule or well-defined rule to write an algorithm. How do you measure the novelty of the algorithm? That is also a critical question. For that also, you look at the algorithms that are there in the literature related to your problem, how they are making difference. The difference is what we mean by novelty. For example, to solve this ImageNet classification problem, there are many algorithms available in the literature, right? Starting from the very first LexNet and till today, so many nets are there, and all are solving the same problem. But you can look at their architecture, how different their architectures are, and that is what novelty is. So similar differences you have to bring into your algorithm. Right. So coming to this hyperparameter tuning, hyperparameter means what? Some extra parameter that are not learned through the network, right? And for instance, you use two networks, right? Maybe one or two models, one SVM and the another one is one random forest, right? And you are using some hyperparameter to combine these two. For example, it take some 75% weight of the random forest, 25% of weight of the other model, and sum them up, right? And based on the sum, you decide whether it is positive or negative, right? So the question is that why do you give 75% importance to random forest, 25% importance to SPM? Why not the other way? Or why not some other values, right? That is a question, right? So here the hyperparameter is weight for the SPM, the weight for the random forest, right? That you can learn. Learn means by using trial and error method, right? There are some algorithms like genetic algorithms or ant colony which can be used for finding these weights, or by trial and error method, you can try out various combinations, see for which combination it works well. That you can fix. These are the ways in which you can tune the hyperparameter. And in neural network, in Python also, there are some built-in functions for finding the good hyperparameter values. There is an algorithm called random search algorithm that will take values randomly and substitute in the hyperparameter place and see the performance good or not. If it is not good, it will change to some other random value and so on. For the value which is for which the network gives or the model gives good result will be considered as the final values of the parameters.
Thank you, Professor. Thank you very much. Professor. Thank you.
Thank you, Professor. Thank you very much, Professor. Shall we close the meeting, Professor?
Yes, ma'am. Thank you.
Yes,
Thank you
thank
all.
you,
Good night to
Professor.
all. Bye.
Thank you, Professor. Thank you. Thank you all.